problem. I have already supplied that PDF file for their reference, but I want to remove this. So if possible, please. Yes. Okay. So after removing that, your case should look like this. You have 0, constant data, and system, and then use set fields. First, before that, you need to make the mesh. So you need to do block mesh command. Right. So this has typically created a block mesh file. It has read the block mesh file and converted into OpenFOAM readable mesh. And after that, you need to do set fields. First step is block mesh. Second step is set fields. Sorry. Okay. Yeah. We are using set fields as I've already initially I explained. In the previous link cavity, all the internal fields, that is initial condition, was same for every cell. Today, what we are doing is we are picking up some of the cells from the left hand state and initializing with some value. And on the right hand side, we are initializing. So that is the utility to give the if else statement that I've already explained already, right? So it will pick up the left side, set some value, pick up the right side and set some value. This is kind of initialization, yes, because this is an initial value problem. Yesterday it was steady state, you initialize with any value, it doesn't matter. Ultimately, it will boil down to a steady state problem. But we need to track this. Row central form is again a steady state unsteady solver. So we need to track our solution with time. So we need the initial condition properly to have a meaningful solution. So this is what we are doing for the initial value problem. Then the next step is to run the solver row central form. So there is problem in your bash RC probably. Please check if you have. Can
change it to adjustable runtime.
sorry. After that, what you need to do? That's what.
Which file to edit?
Control D. Yeah. It's not CD. It's a file. It's VI. Somebody has manipulated the bash RC. It's very difficult to do that. I'm sorry. Somebody's playing with that already. Just a second. What you are running block mesh, right?
Sir, I have a
You
question.
remove this file rm minus rf. See, the best way to remove any file is you rate rm minus rf, right? Since this n is capital, you hit tab, right? Just remove. You have put a forward slash over there. That's fine. You have to put
When I did LS agree, I don't know why it's happening.
there must be some problem. So after that, you need block mesh. After that, set things, and then close it. It's a command. Whatever I'm typing and then hitting enter, they are all command.
Sir, I have a question
That
about
is a solver.
SafeX.
It will fetch the .c file from SRC that I've already explained yesterday, and it will fire all the calculations and then get a solution. So after you hit enter, your iteration must look something like this, right? So this is the output of all the iterations and the residual. Since this is a Gauss Seidel iteration method, it is not showing any outputs. And you have generated time steps at 0.001 spacing. Now you want to download this data to visualize in ParaView. I'll use WinSCP over here. I'll again log in over here. RM minus RL. मैनुअली यहाँ पे इधर जाओ उस करंट डायरेक्टरी में, राइट क्लिक ऑन दैट, डिलीट। कौन नहीं कर पा रहा, नहीं कौन नहीं कर पा रहा, हु इज नॉट एबल। RM minus RF space, हाँ हाँ, forcefully remove that. That's what I was telling earlier. In control dict file, you need to make that as adjustable runtime. In control dict file, that entry, if you can open that system inside, go inside system, CD system. Where are you right now? Go CD, system, VI, control dict. Open it. All right. Inside there, right control is adjustable. Instead of that adjustable, right adjustable runtime. Yeah, run is, you did not save it probably. Sorry.
How to save that?
Right, you type over here. Have you typed? Go into insert mode. Press I. Press escape once. Escape. Go press I now. You are in escape mode now. Press I. Insert I. Okay. And go downstairs to that particular entry. Press escape. Colon. WQ. W and Q. And hit enter. Now, again, if you try to open it, it will show it is written. Open it. Please open. Adjustable runtime. Again, for exiting, press colon and Q. No, it's not. It's okay. It is saying. This is probably version issue. Somebody might have played yesterday with the bash RC. I am not sure. Tested yesterday, it was working fine. First remove this, it's not required.
और ये डिलीट भी नहीं हो रहा है।
Deleted.
Six streams. Oh, अभी हुआ है।
Block में हुआ, हो सर.
दो सेंटर।
Space डालो, capital N डालो, tab दबा दो, it will pick up.
ये कैसे हो आ रहा है आपको?
कुछ नहीं, RM minus RF.
हाँ,
N was capital. You put tab,
okay.
so it will automatically pick up whatever entries are there. And then basically this is the Windows file. So Linux does not allow the spaces in between. So space ke jagah, what it is doing is numerical slash method slash. So it is filling up that space. So it is manually not possible to type that colon. What to do is you press tab, it will automatically pick up and remove that file. Yeah, just press tab. Like if you have a new write numerical, it has already removed, so it is not picking up now. And then press tab, it will automatically pick up, right? And after that, you need to do block mesh. Again, it's a problem for sourcing.
Sure.
Then after that, you need to do set field, and then run the solver. Sorry,
ওটা এলএসি হবে, ওটা 11 হবে।
I was mistyping it. Okay, so I have downloaded my case setup file over here. Now I want to open it in ParaView. Like before, open ParaView. So this is typically what it will look like after you run the simulation. Yeah, this is what you need to do. But what is this? Sorry, this is at 7th second. You go back certain steps back, go over here, you can play the. Basically, so typically, this is what you are interested in looking at. Again, this is a validation. Its analytical solution is available. The red line that you see over here is typically the analytical solution. And since I said there are 4 different combinations, there are multiple reconstruction schemes. We use Vanlier for now. There is MinMod also, and KT with Vanlier and MinMod. You can play with all those combinations and see which is the best suitable numerical schemes for you. So you can make this line plots, but first you need to extract the data in ParaView. So this is typically density in kg per meter cube, and it is varying between -5 to 5. So this is along the axis of the shock tube. The density is variation is along the axis of the shock tube. And if you open ParaView, again go to filters, search for plot, and use plot over line. Then hit enter. Orient this line along the x-axis. Since our axis is along the x direction, so yesterday we did a y-axis plot. Now this is an x-axis. Now it is passing through -5. It was passing through -5 over here, and it is crossing at +5 through the center of the shock tube. Now this is the typical variation that you need to save that data. So again, if you see, I want the x-axis as 0.0 or point x, right? And on the y-axis, I need to see the density variation. So typically, this is the plot that I'm interested in, and this is what I've plotted over here in my slide. Right. So again, you can use multiple softwares to plot the data. I'm not going to do it right now because we have already lost some time. So you can, like before, you can save this data as CSV format, create new folder, and save as comma delimited tab. Tab delimited and name the folder or file and press enter. And another feature that is available over here is you can choose to which array you can write. If you need to write velocity, you can write pressure, density individually if you need to space save. So I'm just interested in looking at the density. I'll choose the density over here. And this plot is at 0.007 seconds, and then please save it. So after saving, you can generate this kind of CSV files, and then you can use any plotting software. This is generated using GNUplot. So you can have a bit of control of the line thickness and symbols and all those things. And this is what typically journal accepts for plotting the data. You cannot make arbitrary plots. This needs to be high quality. I have generated using GNUplot. So you can try it on your own. So this was the first case that we have simulated. Okay. The next problem that we are going to solve is flow over the forward facing step. So this is certain h distance. This has some dimensions. And this is some dimension. I've taken up a case setup from Woodward and Colella. You can refer to that paper as well. This is a typical test case for testing the numerical scheme. So flow is happening from left to right, a supersonic Mach 3 flow, right? And this is an obstacle over here. So this supersonic flow will experience this obstacle and it will create a shock, right? And this is a blunt body, it will create an oblique shock. And this is wall over the top. The shock will basically reflect from here and then exit the domain. So typically, this is also an unsteady problem. So we have the profiles of density from 0 to 4 seconds. Or 0 to 8 seconds, if I remember correctly. So what we are going to look at is we are going to generate data at intervals of 1 second, and we will be able to compare our solution with the existing numerical papers that we have already had. So the typical entries inside the 0 folder is, since we are solving, what we have done is we have typically non-dimensionalize the system. So it says that gamma of the gas is 7.5. So in the simulation, we have taken the product of gamma into R as 1, right? And gamma is 1.4. Gamma into R is 1 over here. So, but gamma in our simulation has been set as 1.4. So R you can calculate is 1 by 1.4. So we need to set up, there is something called universal gas constant and gas constant. So universal gas constant is 8314, right? I don't remember the units. It's joule per kg Kelvin, right? So, but you need R of some non-dimensional gas, which will be R bar divided by molecular weight. R of non-dimensional gas is 1 by 1.4. This is 8314. And then you can find out the molecular weight and then you can substitute over here. This is what it will come out. Again, Cp is gamma R by gamma minus 1. We already know gamma. Gamma R is 1. You can substitute gamma R as 1 and gamma is 1.4 minus 1. So it will come out eventually as 2.5. So we have set the Cp over here. Enthalpy of formation is 0. Again, this is an inviscid case. 0 viscosity and Prandtl number is again useless over here, but default entry is 1. So even till now we have seen only simple geometries like a square one, right? And declaring its point was pretty much exhaustive. You need to specify 8 different points. Now what you need to do is you need to identify the blocks over here. These are the blocks. So for each block, that cube will fit, right? So for each block, there are certain entries of the points. You need to define vertices over here as well. So if you plot all those points properly, or if you are able to visualize it, these are the points in the front and back plane. There are 3 blocks over here. Formed by, need to specify the so what we are typically doing is we are declaring this particular box that I've made as block 1. This is block 2 and this is block 3. So per block, we are basically discretizing with number of grid points. 48 over here, 48 cross 16 in y direction. Again, this is 48 cross 64 in y direction, right? And this is 192 cross 64. There are three blocks over here, and with that we are constructing the geometry. So you can appreciate, like, even if the geometry is little bit complicated from the previous one, we have to take care with multiple blocks. If you want to solve very complex problem, block mesh is not advisable. You can use basically fluent mesh to form command to convert the ICM mesh to fluent, open form readable data. These entries are typically, now we have two different faces over here, right? And I've already explained. This is the inlet patch. So basically it is comprising of two different faces. So we are clubbing them as inlet. This is symmetry, right? This is inlet. This is top again as symmetry. And this is outlet. I don't have the time to explain like how the faces are selected. If you plot those points, make a good diagram out of it, number these points, and then select those particular faces, you may come across these entries, right? So this is already there in the default settings. And again, if we go to system FE schemes option, these are typical entries that we have already discussed now. Again, I'm using KNP with Vanleaf to see the data. So to run the case, since this is initialized with free stream pressure, inside the domain, mark is 3, pressure is 1, I guess, and temperature is 1. This is all non-dimensional values. So for first step, we don't need to initialize the data, so we will simply use block mesh. Again, please remove this file. Again, please note you have to customize according to the .com version. So we have converted the block mesh dict into block mesh file, and then simply use row central form. It will take a while to complete. It's a long simulation. Yeah, do that as well, because version has changed. So typically you are generating something like this up to 8 milliseconds. I'm not running the full simulation. And basically I'll download the data over here. It is basically this PDF file is interfering with the simulation. So remove that RM minus RF, you do. No, keep it over there. Press LS. Press write RM space minus RF. RF. Don't put space. Minus RF space. Type capital N. Type capital N. And press tab. It will automatically figure and hit enter. Do the LS, it will automatically remove. It will remove everything. Right now, you try to. You don't need to change this one. You need to change this adjustable to adjustable run. Adjustable run type. This is cap, yeah. Cap, and then again time is cap, yeah. Save this way. Now, please open the data in ParaView like before. So this is what your data will look like. Change it to density. So it is flow evolution with time. So you can play a nice animation also here. So typically, if you run the solver, it will again evolve into flow structures. So this is a bow shock, and then the bow shock is reflecting from the top surface, and then it is reflecting back inside the domain, right? So for creating line plots like this, which we call them as isolines, right? This is the data pickup from the simulation from the previous papers, and this is our present computation. So if you want to make line plots like this, first you need to search for a filter which is named as slice. You enter apply, and you need to make a slice in Z normal direction. And then again click apply. So basically what it has done is earlier our data looked like a 3D data. Now after we have sliced it, it has converted into 2D domain. Right, this is the slice. Now we need to make the isolines. So for that, another filter is there, contours. And inside this contour, there is an option. What it will do is this is what we call is that as filled contour variable. It is filling with colors. We need to make black and white lines of isolines, right? This is density equal to 0.8. So wherever 0.8 is there, it will connect all those points. Then density equal to 1. So again, there would be some line passing through this near to this. So shock is basically contained between some range of, let's say, 0.5 to 1. So we can play around with this. Generally in papers, what they do is they specify the range. Rho is varying between, let's say, some lower value to higher value in intervals of, let's say, 0.1. So you can give that number over here using this range command. So this is the lower value. Let's say I use let's say I use 5, and let's say I use 15 over here. So it will generate a matrix with 10 number of samples and hit apply. So the body is not visible. But it will typically look something like this. You need to switch on the body also inside the first and then select outline. So you can play around this particular range and you can get contour lines something like this at different instead of time. So we see our solver is typically is in good match with the qualitatively in good match with the previous results. So this is how things work out in CFD. You have done till here, right? Then inside the first in the pipeline window, go to this eye icon over here. Switch on the eye icon. It is earlier surface, right? It was like this when we initially loaded. So instead of surface, use outline. Or use feature edges to be more precise. Again, you can make a animation out of it if you want. So this is how typically a flow will evolve with time, right? So you can, this is an unsteady solver. You can make movies, animations of the solution. This has been generated using TechPlot. I have not used ParaView. So it is up to you how you do it. The third case that we are going to look is supersonic flow over a compression ramp. तुम्हें वो basically वो paper का range I'm not able to recall right now. They have given one range, so it is just for testing purpose, right? In the paper, if you go and refer back, that is just a demonstration. That range has been properly set up using the values that they have provided in the reference paper. You set that reference paper, you set number of contour variables, it will automatically trace out all the contours. The PDF that I made you delete that. The basic purpose was that I have taken all the data from that particular paper. So you can refer to that paper. I'll again share you again. The next problem is Mach 6 flow over a 15-degree wedge. So basically, this is a flat plate. And this is the compression corner of 15-degree. And this is again a wall. So in the viscous simulation, if this case is invested, it will encounter a turning and there would be a oblique shock wave, right? But in viscous case, there is a boundary layer separation, and therefore this complex shock wave pattern occurs. There is a separation shock and then reattachment shock will match further, and then it will form a shock structure, something like this. And its experimental data is available from Marini. CFD data is from John et al. So this is basically the formulation of CP, whose formulation is given over here. This is the geometry in meters. This all mesh I have provided in ICM file in this particular folder. So if you go constant, and open thermophysical files, so in high temperature cases, CP and CV will be a function of temperature. It will no longer remain constant, and consequently gamma, which is CP by CV, will be a function of temperature as well. So last time we used CP as some constant value of 1005. If you use that, and in the high temperature cases, if you do the simulation, it will basically not give the correct relations, or it will diverge. So what we do is we define CP as function of temperature using JNF polynomials. So typically it is like A0 plus A1 T plus A2 T square by 2 and so on. There is fifth power polynomial as well, 5, A5. So the temperature variation is accounted into a simulation using JNF polynomials. And inside that also there is diffusion. For some ranges, let's say this is applicable for some temperature range T1 to T2. This is what we call is as T common. And the same T2, there would be equality over here, T2, T3. So this is T low, this is T high. There is another set of polynomials for this, right? So for these two temperature ranges, there are two polynomials, one representing high CP coefficients, that is valid for higher temperature range, and one representing low CP coefficients valid for lower temperature range. You can take the temperature range T1 to T3 and construct a whole polynomial, but that will be giving a bit of error in your simulation. So it is better to make piecewise polynomials. HF is enthalpy of formation. For air, it is 0. You don't need any enthalpy to form, right? You can use, recently we use Cantera, a software that can be compiled with Python to obtain the, Cantera contains the database, right? At temperature, let's say if you have 100 Kelvin, what is the CP? It will fetch that, right? At temperature 110 Kelvin, it will fetch the CP. So you can make a table out of it, use the regression formula in Python, and you can obtain these coefficients, right? But in default cases, most of the cases in OpenFOAM, they come with the by default coefficients. If you want to change this, you can use Cantera. For air, these coefficients are valid. You can pick up any species, nitrogen, oxygen, carbon dioxide. If you go to combustion tutorials, you will find a lot of CP coefficients. You can copy paste and use it in your simulation. Yeah, this is a structure. It is, again, it will take some enthalpy offset, some another constant and another constant, which is for entropy offset. So this set of coefficients is basically what it is you have to pick up. This is A0, A1, A2, and then other two coefficients. For this is valid for high temperature polynomial, and another is valid for low temperature. And this is the temperature ranges: 500 to 1000 low CP, 1000 to 5000 high CP, right? And now the transport properties which I was talking about, in our simulation we have kept Prandtl number as 0.72, and the Sutherland equation that I was talking about, as t to the power 3 by 2 divided by s plus t, or ts plus t, right? Ts is 110 for our simulation, 110.4, and as is 1.458 into 10 to the power minus 6. So this is Pascal seconds. Unit is Pascal seconds of this whole expression. So these constants, remember, are valid for air and nitrogen. For other species, let's say if you want to solve for carbon dioxide or oxygen, so this constant you need to find it out from literatures, and you need to substitute accordingly over here. So now what you can do is, again, I will remove this PDF file, would require it. Okay. So I have already supplied the mesh using block mesh file. Again, the principle remains the same. I'll not explain all the entries now. This is one of the block B1. This is another block B2. You need to identify the coordinates. I have already supplied one PDF or PPT file with you. You put those coordinates, make two blocks, discretize with ny number of points and nx number of points. Let's say this is nx1 for this block, and then for this block, this is nx2. So this block is nx1 by ny, and this block is nx2 by ny. So this ny remains fixed, right? And you can use grading also. If you want to make very fine mesh over here, so those entries I've already fed it in, and gradually you will increase the spacing as you move away from y. Right? So you are capturing all the interaction process over here without, if you want to use uniform mesh, then unnecessarily you will discretize this domain as well, where nothing is happening. And typically for the boundary condition, this is pressure, velocity, and temperature. It is fixed at free stream conditions. This is far field. This is outlet. And this is, these two boundaries are walls. That is, it is no slip and zero gradient temperature. That is isothermal. Adiabatic wall. These are the typical boundary condition for solving this type of problem. I have already simulated that problem prior, and I have given the latest time step. Since this is not just 1 day simulation, it will take like around 1 week or 2 weeks to complete the simulation till that point. Because time step, because of this high velocity, it is roughly around 1380 meter per second. Which is, if you can appreciate, it is 1.38 kilometer per second, right? So since this is very high speed flow, CFL number for stable simulation is between, you need to set the CFLs between 0.5, less than 0.5 to be very precise. If you go beyond 0.5, your solution will diverge. For stability, this is the requirement for O central form. So I've kept my CFL number as 0.2. This is very standard practice. Don't go to this particular extreme, although it is valid. But as I said earlier, the solution will start to oscillate if you go beyond that. And if you take very high CFL number, it will diverge and corrupt your solution. So I have taken 0.2, and with this 0.2 CFL number and with this high speed, my delta T or time stepping is in order of 1e minus 9 seconds. So you can appreciate like how small this time step is to calculate the solution. The compressible flow is basically having this drawback that it brings down the time step to very small time step because of this very high speed flow, and it will take even months or 2 or order of months to complete the simulation. So I've already provided the test case setup and the converts file over here, which is at 3 milliseconds from the start of the solution, right? One of the important thing is I have supplied this case with decomposed paradigm. So what it will do is it will divide the subdomain or domains into various subdomain. This is my computational domain. What it will do is it will decompose the solution into various number of blocks, right? 40 of these blocks, and each processor will handle these blocks if you run it in parallel. So yesterday, sir was telling that you need to supply adequate number of blocking such that communication loss is not there and there is speed up also. So with the hit and trial in Param Shakti and Param Sanganak at IIT Kanpur, 8 blocks, 4 to 8 blocks are sufficient. Or let me put it in this way, the number of spacing or the blocks, number of grid points that one processor can handle should go roughly around 10,000 to 15,000 cells, or maybe 20,000 cells. This is just a rule of thumb. But you need to find out the optimum number for your machines. So with that number, if I put 40 is over specified over here, I'll just put 4. And after setting this file, I'll run decompose par. So now if you do, it has 4 different processors, processor 0, 2, 1 and 3, 1, 2, 3, 4 and 0, 4 different processors. And if you see inside the processor, it has taken up this time step, converse time step, and it has decomposed into 4 different blocks that I was talking about, right? And it has taken the mesh from the constant and it has decomposed it. And for running the file again, all these entries were explained yesterday. I have already set the script file for this. Need to use sbatch run reservation.sh. And if you do sq, somebody has already fired the run from 2 minutes. So I fired my run. You need to note your ID number since this is a shared account. So this is creating conflict. If you would have an individual account, you can track all your job IDs, specify the name accordingly, right? Name of the test case. And then if you want to see the output, do tail minus f log dot whatever log file you are writing. So this simulation is running. It will run until 0.2 seconds, right? So ultimately, what we need is we need this zero constant system. I'll go out and download the data. And I'll open this data in Paraview again like before. So this is the converged solution that we have, right? If you see the velocity, at the bottom there is a separation bubble over here. This is the viscous boundary layer that is growing, and there are shock waves, weak shock wave, leading edge shock wave, reattachment shock wave, separation shock wave. All those features are basically calculated over here. So what you need to do now is you need to validate again this data, whether you have done it correctly or not. So you need to make pressure versus x direction coordinate. This pressure is non-dimensionalized with respect to the formulation that I have already given, Cp, right? So Cp is P minus whatever pressure you have calculated, subtract that with the infinity free stream pressure, which is 191.4345, divided by 0.45 into gamma into again this pressure, and Mach is, for this case, if you calculate, it is 6. So if you use this formulation used in Excel, you can plot the data something like this. I have already provided the data of John et al. And Marini et al. You can use any plotting software, as I have already told you, and you can obtain this kind of plot. For extracting this data for the present computations, what you need to do is, it is little bit tricky. If you can, if there is any problem, please halt me in between. Please ask me in between. First, what you need to do is you need to switch off every patches that is there. Since this is the wall pressure distribution, you need to switch on the wall, just the wall, which is bottom patch. And the obstacle patch. This is the wall that I've created using block method, right? Then search for a filter which is named as merge blocks. You need to do it because we need to find the distribution over this whole surface. If you just do the plotting individually in each of the surface, you need to append manually. So merge block, what it does is it will append these two patches first, and then we can basically plot the data over this particular patch. So hit apply. Don't need to do anything. Now this is a single patch. Now again go to filter, search, plot on intersection curve. So what it basically do is that plane, we need to find out z direction plane, z normal plane. It will find an intersection with the patch, right? So whatever line it will come, it will plot over that line. So you need to hit z normal and then press apply. This is the typical variation of the pressure over this whole patch. So like before, you can use the stream-wide coordinate, point x, and use the pressure, right? So this is typically what it has been plotted over here. You can see there is some spurious oscillation, which is undesirable. So you can play around with a lot of numerical schemes that is available in OpenFOAM to bring down these oscillations. But the cost that you will pay is the shock structure might get little thicker and separation bubble will basically deteriorate. So the best solution that I could obtain with is with the KNP scheme with Van Leer reconstruction. So you can now hopefully run the compressible flow simulation using Rho Central Foam Solver. There are certain customized solver also available. If you go to GitHub, you try to compile the solver, but you need to install specific version in there which they have coded. So it is up to you how you proceed further. This was the basic glimpse just of what compressible flow solver is all about. So if you have any queries, you are free to ask me, and then we can wind up the session.
Hello.
Hello. Not just this, even on yeah. Uh, Hello, online participants. Can you confirm me whether I'm visible, audible, and screen is perfect, changing? Can you just message us? Yes, wonderful. Oh, thank you so much. Okay, Dada. Don't worry. Thank Yeah. Hello, everyone. This is Raja from IIT Kharagpur. I work as a faculty member at Mechanical Engineering Department, and I mainly work on turbulent flows and turbulent interfaces, which involves with multi-phase flows. So this is a vast subject. I will try my level best. First of all, to give what exactly we are trying to model, whether even it is possible, whatever we model possible via OpenFOAM. It's not that OpenFOAM is some God's given kind of gift. Some of the possibilities are there and what kind of problems we can model, what kind of problems we cannot really model, even if we use OpenFOAM. It's not just about new solver developments, even existing problems, how far we can really go. And in the afternoon session, we will have a couple of examples, 4 examples on multi-phase flows we will try to have. It's audible, but someone is saying, fine. Oh, I see. Okay, great. So the first part of multi-phase flows I will cover. In the afternoon session, a little turbulence simulations, one of our TAs does, Dr. Abhishek. And couple of more examples will be done by our Dr. Anurag and Dr. Snehal. And after that, again, I will continue. That's the plan. Let us see how far, first of all, we can really go with these multi-phase flows and what are the solvers at least available at OpenFOAM. So multi-phase flows means if you are picking something like gas turbine engines, there always be some air, fuel will be injected. When you are injecting fuel, tiny droplets, it may break up. That is the thing what any chemists or chemical kinetic guys look for. Break this jet into tiniest kind of pieces so that it actively participate in chemistry reactions, generate heat, high pressures, and so on. While it is burning, it's not just fuel droplet, but you will always have something like soot, carbon deposits, and many other kind of things really go. How they will interact. If someone even simulating compressible flows, okay, I have OpenFOAM, I have solver, you may be in a position to really understand shock dynamics. But whenever this soot kind of particles are coming, vapor deposit is coming, maybe droplets are going, it completely affects additional things. And in fact, compared to your typical shocks, those actually leads to additional effects. These are the primary effects in some sense. Your entire primary shock will be led by this sudden fuel droplet creating heat and additional discontinuities in the system. So that kind of things also to be modeled at multi-phase things. Maybe if you are picking nuclear reactors, there always be something like boiling happens, steam goes, condensation kind of things, choking kind of phenomena, many other kind of things happens. One has to be careful there. So your multi-phase simulations, whatever we do, has to account those kind of issues. Similarly, if you are looking at processing kind of industries, chemical processing kind of industries, there always be fluidized beds to participate, better alcohols, maybe better drying kind of race one would like to achieve. You will always see multi-phase flows. Even if you are looking environmental kind of issues, something like hydraulic jumps, you will have many kind of complex interfaces usually involved with turbulence. This is the first thing. Even offshore structures, when you are looking, the waves is not just about turbulence. The wave, their impact also natural choice for these multi-phase flows to go interact with these structures. Some of you guys must be working on these wave structure kind of interactions from civil engineering groups. For them, that kind of multi-phase flows are important. Similarly, if you are looking any weather forecasting and other things, naturally the large scale cyclones to be resolved. They always have this condensation, sudden heat release, accelerated kind of motions, interactions happens. These are also part of multi-phase flows. Okay. Ah, I don't know why it is looking a bit terrible, but usually multi-phase flows means you will have liquid phases, solid phases, gaseous phases, they interact with each other. It depends on which domain you are working. Maybe some people really look for liquid and gaseous kind of thing. Some people look for gaseous solid kind of thing, like pharmaceutical kind of guys who wants to dry the pellets. Maybe solid granular kind of particles people are trying to look for. They mainly look for gaseous solid kind of thing. Some people look for liquid, solid, gaseous kind of thing for petroleum refineries and so on. The main thing in these two-phase flows or multi-phase flows is there always be interfaces. These interfaces, gas to liquid, maybe liquid to solid to gas also happens. Okay. Thank you. There always be something like interfaces, momentum, energy exchange happens. And these three things coupled interact with each other, one has to resolve. So especially in today's thing, what we are trying to look at, couple of solvers, maybe one important solver, which we call interform for gas liquid phases. This is the thing what we are going to look at. Though we are saying multi-phase flows, handling gas to liquid, liquid to solid, solid to gas, you have different kind of solvers. And it's not just one solver, which will be suitable even for gas liquid kind of thing. It has different varieties. That's the thing what we are going to first of all have broader perspective. Even if I am saying something like interform, is that generic or much better things are there, the terminology. So let us look only for gas liquid kind of thing. There always be something like disperse based on how much gas flow rate is passing, how much liquid flow rate is passing. This is what we call superficial velocities within a given cross section. If you are taking at entrance conditions, how much gas interacting with liquid. Based on that, you will have completely different kind of problems, different solvers exist. So a one single multi-phase flow solver, I take it, my entrance conditions are this is not correct choice. So based on how much entrance velocities, the liquid fractions coming in, how much gaseous fractions are coming in, within the columns, tubes and other things, you may have to tweak to multiple different solvers. That's what we call something like based on very low fractions. You will have bubbly kind of flows. You will have dispersed kind of things. You will have annular kind of flows. You will have churn, slug kind of flows, stratified kind of flows. For all these things within the same problem happens. That means there is no unique solver. You can straightforwardly use it. So something like there is water or oil is passing through a pipeline for a refinery. It always contains certain contamination like the soil, the mud, maybe other kind of two different kind of oils, waxes, many kind of things are passing through that. Within the same pipeline from the shore, wherever that refinery kind of structure, all the way to supply location, many complex kind of multi-phase phenomena happens. So one has to use a solver depends on which zone they are trying to look for. You can't really simulate the entire thing. Depends on what you are looking for. For example, even for gas liquid, something like you have some refinery, maybe even something like milk, you are trying to transport into milk container. There always be something like nozzles and that milk really goes into the system. The surrounding air get entrapped within that liquid and tiny mist kind of thing happens. Sometimes they may evaporate also. And while it is entraining, you will have gaseous bubbles and shaken up and so on things happens. If that happens, one of the best solvers is model via Euler liquid, Euler gas without interfaces. Though the problem has certain interfaces like milk or oil is coming, immediately it is interacting with the air. A complex kind of state like bubbles, droplets, spray, mist kind of things are happening, again going down. The volumetric flow rate, this is easiest problem to visualize. But in pipelines and other thing, you need to maintain certain pressure gradients. You need to apply certain entrance flow conditions. Without that, you can't achieve the required transport rates. So when you are trying to do that, one of the easiest possibility is going with Euler liquid. That means you already know what it means, discretization, governing equations, and so on. Even though multi-phase flow system, we do not have precise governing equations of the problem. This is in some sense approximated kind of things what we are looking. It's not like typical fluid mechanics where you have my Navier-Stokes equation. I can write it momentum equation even at each point by control volume analysis and try to really link it up, write it is not that straightforward in multi-phase systems, even for solid liquid kind of thing. And you will see this kind of multi-phase systems in engine chambers like gas turbine engines and other kind of things, most prominent kind of feature. You can't ignore that. But still, we do not have models for that. The easiest model is I really don't care about all these kind of interfaces, but I will treat one liquid as one Euler phase, another liquid is another Eulerian frame, club them with some terms, or don't club them with the terms, try to solve it. If that kind of things are happening, these kind of systems called Euler kind of phases, multi-Euler kind of systems, two-phase Euler kind of systems. Based on that, you will have two-phase Euler form, you have multi-phase Euler form, and its kind of variance. So not unique kind of solver. Sometimes you may have to capture interfaces. You are more interested about knowing the constituents like bubbles, drops, and other things. Naturally, you need to bring these interfaces. When that interfaces you would like to really begin, you will have Euler liquid, you will have Euler gas, and some kind of interface tracking, interface capturing one will employ. And both Euler liquid, Euler gas, you club with one particular solver, which you call single fluid formulation. Only interface, either you track or volumetrically you will distribute. Shortly, we will see what it means. That kind of techniques, volume of fluid method, front tracking, level set kind of things, what people try to use. Maybe your application is something about marine kind of things. Marine propellers always be subjected to cavitation, pitting kind of thing. So these Jane Jatic propellers, if you are looking, any Amazon products mostly come from China, they don't get shipped. Usually there will be sea routes via shipping kind of things happens. Any products, shipping is the most important business where you will always run via these propellers at the behind. And these will be gigantic like a 3-floor kind of propeller kind of sizes, what you will see, 2-floor, 3-floor kind of thing, something like 10 meters, 20 meters kind of diameter, casted kind of thing properly taken care of. Huge expenditure happens just because you make it to run it fast in the local neighborhood, some kind of phase change happens in the liquid. Whenever you are going to create very low pressures inside the system by momentum driven kind of thing, because your propeller is moving very fast, locally a kind of suction created, immediately your salt water start evaporating and you start sensing tiny bubbles. Ice may be recognizable to see that. Sometimes these bubbles will be some 10 micrometers, 20 micrometer kind of sizes. Ice may not be in a position to really detect. Millions of bubbles created around these propellers and start bursting, creating shock waves, and complete material will be eroded. That means within soon 6 months, 1 year, 2 years, you need to replace that entire big 50 meters, 40-meter kind of propellers. So for that kind of problems, you can't go with Euler liquid, Euler kind of systems, because these are millions kind of bubbles interacting with each other. What people go with Euler liquid, Euler gas, you need to account bubbles. These bubbles may be point kind of bubbles, which will grow, condense. So you need to have additional kind of things. So we will see something named DPM kind of particle trackers, dense particle kind of foam and other things usually employed for that kind of thing. So the same multi-phase flow systems, if you have that kind of applications, you will use Euler kind of thing, we will see. If you have the same application with little complexity, you will have Euler with interfaces. The same problem, but millions of bubbles are also coming because that phase also present, liquid phase also present. You will go with Euler, maybe with additional points. If you have chemistry, like sonochemistry happens when these bubbles are bursting and other kind of things. Again, you need to activate those chemistry modules. It's not straightforward, it's jumping around the solvers. The same problem, splashing, for example, like agricultural kind of guys, they always worry about the seasons. Rain happens, wets the soil. Whenever there is a soil really wets, immediately there will be spray ejection happens, the aerosols. Whatever the top soils which they sowed or planning to sow, because of this droplet kind of impact, the soil really the aerosols really start spreading and entirely spreads. You will sense that kind of smell. For that kind of things, solving the problems, the chemistry, the nitrogen, the bio kind of material which really spreads, people will be interested. Maybe even COVID kind of things like pathogen. Chemistry kind of thing also becomes important. That modules will be completely different. So one has to be careful. And even at that kind of level, there will be additional things like resolving discontinuities becomes non-trivial because equations are not available. Something like all the time you have a phase, liquid, gets stretched, sudden like faucet, like kitchen, if you open something like a kitchen faucet or tap, liquid stream really comes. Suddenly at one point, the liquid really breaks and the droplet really goes. How do you really resolve for chemistry kind of or chemical engineering kind of applications? You do not have equation when it is separating out. So one has to propose the equation to capture it, what is happening. So again, that will be a bit more challenging at multi-phase systems. When you have fuel sprays, the engine directly, there will be jet really comes into the picture. Variety of structures like ligaments, interaction, droplets, immediately evaporation happens. And this kind of simulation, just one spray kind of thing on supercomputers goes for at least 1 week to 10 days kind of on 1,000 cores kind of systems. People really worry about what is the best solver, whether it really resolve, whether that really helps to understand this breakup, the engine sprays. The main thing, they always be multi-scale. That means you may feel like my mesh is wonderful, I have refined. You will have certain locations require more meshing. That changes with the time and space. You can't something like a static mesh. I have very refined mesh. Maybe this zone is important, wall boundary layers, I'm going to resolve. But these filaments, ligaments, droplets start moving here and there. So one requires that mesh is adaptively moving. So there always be issues like how to really employ these adaptive mesh refinement kind of things. There will be something like chimera kind of meshes, which will be mapping. It's a bit challenging kind of task. These are the things what these multi-phase flow guys really look for. For example, I'm picking one example here, the same spray cartoon. Engine chamber, some hydrogen, liquid nitrogen kind of things. One is interested to understand. To do that, naturally, you may apply some boundary conditions there. Maybe something like having some kind of mesh discretization. The liquid portion, you will be in a position to really resolve. But these droplets becomes fine mist over the space. When you are having such kind of thing, your mesh supposed to resolve more, that will always contain some kind of tiny other kind of varieties. They may again interact, become larger. So one requires more meshes. Is it that good to have more mesh dynamically moving, or the strategy is supposed to be have more mesh, but if it is going to micrometer kind of thing, should you really treat them like particles? That kind of capabilities one requires till now. Your OpenFOAM or any kind of softwares are not exist to handle such kind of problems. You always approximate, like what sir yesterday said, whatever you do at engineering in some sense is approximation. It's not true picture. Because when it really goes to the smallest things, how to handle, your communication lag naturally comes onto the computers. Are you really going to save all that fine missed data to go for next time step calculation? It's not that easy. So alternative strategies are required for that kind of problems. And no universal method. So just to get into OpenFOAM kind of stuff, the solvers, if I put overall picture, this multi-phase modeling itself is naive. You may have solvers, very well established fluid mechanics, compressible flow kind of thing. By definition of multi-phase flows, they are compressible in nature. They always allow shocks, discontinuities. Usually people either go with molecular modeling, mesoscopic modeling, or macroscopic modeling. If you are going with molecular kind of modeling, each of those molecular kind of size one requires to be handled, and no engineering application possible just purely by molecular modeling. The entire engine spray you want to really resolve by molecular modeling, what you will do is maybe around one droplet you will be in a position to resolve in a better way. If it is macroscopic, which we will see in our examples at OpenFOAM level, the VOF techniques level set, two-phase Euler form kind of things, these are called macroscopic things. You don't really resolve, but a kind of whitewash kind of approach you will go. That kind of things we call macroscopic. In between them, there will be something like mesoscopic. You will take some help from molecular, take some help from microscopic, handle it. Usually dissipative particle dynamics now at OpenFOAM they have, and lattice Boltzmann methods. These are the ones which handles both. But each of these grand strategies, they have their own limitations. One cannot have generalized thing. And what we are trying to look is macroscopic modeling. That means in some sense connected with mesh discretization kind of approach what we are going. Especially grid-based kind of techniques. That means you will be in a position to really draw mesh for one of the fluid phase and try to solve your governing equation for that. That kind of things what we call grid-based kind of technique. And in that also something like with interface capturing, without interface capturing. If you don't want to capture interfaces, then we usually have simplified Euler kind of approach. If you are going to capture interface kind of thing, you will have something like single fluid formulation, but interface, you will be in a position to track it. We'll come back when we are going to see that. And what we are going to look at OpenFOAM, because there is no unique strategy, look for grid-based kind of technique, especially on volume of fluid based on interFOAM. One, something like Eulerian multi-phase model, Euler, two-phase Euler, multi-phase Euler kind of thing. Something about particles purely involved, particles clubbed with a flow. These are the solvers what we are going to look for. So even though multi-phase, we have our own limitation in terms of what kind of multi-phase we can really look for. Only gas, liquid mainly, maybe, liquid kind of system or gas liquid kind of system we are looking, or maybe liquid with particle, gaseous kind of thing. So mainly interFOAM is one kind of solver, belongs to VOF technique, volume of fluid method. Multi-phase Euler form belongs to this Eulerian multi-phase modeling. One of these dense particle form, by now you know, Whenever there is end form kind of thing, indicates something like a solver. So when you open your control dictionary, there always be application type kind of thing, solver name will be there. And that's the thing what we are looking for. And that belongs to this discrete particle modeling kind of thing, discrete elements also. So any questions till that part in terms of understanding? Okay, let us move. If no questions, what about online guys? Any questions? Okay. Yeah. Can you speak loud? So basically in fluid mechanics, because whether we say compressible flows, shocks, gas turbines, whatever is the grand strategy is fluid mechanics. The way it has evolved over the time, people always try to construct meshes, apply certain conservation principles like mass conservation, momentum conservation, energy conservation, write something like a partial differential equation, which varies with the time and space for velocity field, maybe density, maybe temperature, something like a field description we always write. We always solve that for given initial conditions, boundary conditions. So this word Euler is meant for that kind of description, which usually people call on Eulerian frame. We are going to write the differential equations on which we are going to understand this density, velocity, temperature, enthalpy kind of things. Correct. So basically when bubbles are there, now if you are going with again gaseous kind of thing as a Eulerian description, mesh kind of thing, it may not be capturing your interfacial effects. So for the purpose, even though it is gas, they treat like pointed kind of gaseous bubbles are present random locations. They may grow based on some simplified model and try to handle like typical Lagrangian means Newtonian equation like F is equal to ma kind of thing. Though it is gaseous, for our at first sight, it looks like mesh must be there gas. All the time I'm going to use Eulerian, but when it comes to multi-phase kind of thing, locally these gaseous pockets are isolated, something like marine propeller when we are looking. Most of the domain it is liquid, but some points you will have gaseous phase. So they try to treat like spherical kind of bubbles, maybe non-spherical kind of bubbles whose center of mass is located at one location. Let me advect it so that they can exchange heat, mass kind of things across them, even momentum. We will see that. So when we do that, we call Eulerian liquid, Lagrangian gas or Lagrangian particles kind of things. We'll see.
Hello, sir.
Particle is more like a keyword in some sense. Means everything boils down to one center of mass so that I can write Newton's equation of motion directly on that. I don't need mesh on that. You require that communication between those particles affecting flow, flow affecting particles. We'll see.
Hello, sir. I have one
Yes, sir.
question. Sir, where we can use that VOF, LSM and coupled VOF and LS?
Splashing head. So it depends on who is working. Why I'm saying is a PhD students, his objectives are different. An industry person objectives are different. Maybe if it is just something like designing nozzle where I should really look, so the splashing really control. I don't want directly the input flow rate coming out should not match somewhere input, somewhere output kind of thing. Splash maybe depends on the application. You will be in a position to really sense whether interform is good enough. If it is good enough, one will be in a position to use it. No, that's not the thing. There are variety of solvers because Interform has its own cons in terms of capturing what is required. We'll see that. So based on the application, the solver is completely different. There's nothing like unique, and even what kind of validation people do, there always be something more where it's not going to work. Okay, great. So shall we proceed? First thing, what we are going to learn is something named volume of fluid method. Two phases there, liquid, air, liquid, such kind of system. VOF, volume of fluids. What exactly that volume we are going to look for? Maybe there is some wave is breaking, oceanic kind of application. In an abstract way, if we are going to really solve such kind of thing, one is interested about how wave propagates when it really breaks, whether it is going to contribute for this climate control, because most of the CO2 get trapped by this wave breaking kind of phenomena. Though we talk about CO2 sequestration, reservoirs, climate change, and other kind of thing, most of the carbon dioxide usually gets stored in this ocean wave breaking kind of thing. Maybe some person is trying to understand how wave interacts with structures for his kind of ship, maybe for his offshore onshore, shore kind of structures. A pictorial way, if we are going to draw in very abstract sense, one requires a lot of mesh, air, liquid. See, complete mesh one requires. In 2 dimensions, you always look for a projected plane. Though it is a 3-dimensional kind of thing with time varies, on 2 dimensions, if you are looking maybe a cut section where wave breaks, this is that abstract wave. Bottom, one fluid, up another fluid. Your eyes are easy to recognize in some sense. Air, water, whenever light passes, refraction kind of thing really sense you. Well, there is something like air, liquid when they are interacting. I can really see some sharp contrast, so that sharp contrast really tells me that is air, this is liquid. For computer, it doesn't know what it means sharp contrast. You need to teach the computer. Sharp contrast means these values supposed to be that value. Density of air must be 1 kg per meter cube. Water 1000 kg per meter cube. But whenever you are solving the equations, trying to club that, there always be errors involved in that. Instead of sharp 1 kg per meter cube, suddenly you start getting something like 800 kg per meter cube somewhere in the mesh. Computer doesn't know what it means 800 kg per meter cube. All the time we believe that air 1 kg per meter cube, water is 1000 kg per meter cube. If I have 1000 kg per meter cube, I will say that this is water. If I have 1 kg per meter cube, I will say air. But because of errors, algorithm, the mesh resolution, many other kind of thing, it varies all the way from 1 to 1000 at every point, every given time. Computer doesn't know. Now, how are you going to really say what is that new fluid emerging out of computation? Some part of the domains within there, 800 kg per meter cube is not oil, still air water kind of mixture. You don't know how to resolve them. That is the place this volume of fluid method really comes for rescue. So at abstract level, there is interface. I can always say that let me put initial some particles, markers. Let me add with these markers. This markers goes here and there kind of thing. So I always say water, air, this is the way they are interacting. But as this wave is evolving, these markers sometimes come very close to each other. Sometimes they're scattered out. So it will be too much load on the computer to introduce more and more markers into the system to all the time capture interfaces. Because millions, billions of particles you need to introduce, advect them. If I do that, in some sense, we call front tracking technique. You will have phase, liquid, air, and also something like marker points, you advect them. But that's bit challenging task, though it capture your interfaces. Without capturing interfaces, you can't transport stress terms from one term to one phase to other phase. Unless these stress terms properly modeled, you don't really simulate the correct picture. heat transport. That boundaries, the stress terms are the ones which are responsible for any evaporation, any condensation, any breakup or any kind of chemistry happens. Interface has to be really resolved. One approach is front tracking, you put markers, but over the time, these markers, when wave is breaking or sharp gradients are happening, more and more particles required there. You need to put them. You need to take out. Itself is big data challenge. So instead of that, what people do is, let me write first of all equations for this phase for this. Only one set of equations I will write. Though two phases are there, I don't really write two governing equations. Only one governing equations I will write for the mass and also for the density and also for the viscosity and whatever the property. However, based on the mesh where I am located at, I will use that particular density. If I am in the liquid, I will use density of that value. If I am in the gaseous, I will use that density. I will use that viscosity for that phase. I will use that particular viscosity at that phase based on which field I am in. So there will always be some kind of control, a field alpha, volume fraction field, shortly we'll learn. If something, one, treat it like liquid. If that alpha value is equal to 0, gaseous kind of thing. Based on that, I will activate. Oh, now you are in air, so use air properties. Now you are in liquid, so use liquid properties. So there always be some control to sense it. And that control, how carefully you will be in a position to jump from 0 to 1. 1 will be in a position to really track what is happening at the interface. If that we are going to do, we call volume of fluid method. Instead of just worrying about interface, now what you are doing is, I really do not have any markers or interface kind of thing. Everywhere, some liquid domain I will have. White kind of liquids, gray kind of liquids. Whatever I need to apply interfacial property like surface tension, I don't apply at that point. What I will do is, I will somehow calculate some kind of gradients, what is happening, put that surface tension values locally distribute on this grid. Here, surface tension must be this value. Based on this kind of curvature, the alpha field really tells you how we are going to sharpen. Apply this much force, apply this kind of velocities, apply this kind of temperature, apply this kind of chemistry. So something like fill liquid everywhere, volume of fluid, the entire volume you will focus, gray color, white color, some part is gray color, some part is white color. So I always sense how quickly that alpha field or color variation is happening in that mesh. Based on that variation, I will be in a position to apply the force and redistribute it. That kind of approach in very abstract level, what we call volume of fluid method. You don't track any interface. You fill liquid, how that liquid color, in some sense computer language like alpha 1, 0 is happening. Based on that, locally estimate volume of this surface tension force, estimate it like volume force, add that at your momentum equation. So you will have your typical Navier-Stokes equation. Instead of applying a surface force, you apply a volumetric force on the system. This equation applicable only for those tiny volumes. You always apply finite volume technique, means you will have mesh within that, how much flux comes, how much flux really goes, and so on. That is the way you balance. So anything, whatever you write the equation, per unit volume you will write, and how much comes, goes, and so on. But when interfaces are coming, these are surface kind of thing. That entire thing has to be converted like how much it can apply on a volume. Some kind of averaging to be done. If you do that, apply that, there will be some force, surface tension. And you solve only one kind of equation entirely, whether it is water, whether it is air, one equation only. One equation means you have one particular momentum equation like x, y, z kind of momentum equation for one particular phase, but that phase property carefully you tweak it by changing your density or kinematic viscosity in those phases. Now, to do that, what people try to do, though you solve momentum equation, mass, whatever this kind of thing, you try to add one more equation, which we call transport equation, alpha, that function f, something like on one side it has 0 value, on the other side, think of from the top view. There is some droplet or bubble is present. From top view, you will see some kind of interface, and there will be liquid, there will be another liquid. So it has one particular value, the transport property. It has another particular kind of transport property. Can I really get that kind of transport property by advecting an equation? And that's the way you really decide whether it is fluid 2 or fluid 1. In addition to your equations, you will bring one more equation for your volume fraction field. Just to put abstractions, the red line, whatever you are seeing, is one particular phase. So something like, think of, there is some droplet inside another liquid. You are trying to look at how the density varies, or perhaps how the property varies in the droplet to in the air. The density of the droplet is high compared to density of air. So that way you can really think of maybe one particular density in this space. This entirely droplet is present, density is constant, is supposed to sharply fall. Again, another density is supposed to have. But when you are using any kind of multi-phase flow, capturing such kind of sharp discontinuity is not possible, even under low Mach numbers. Maybe sometime back, you must have solved compressible flows. Whole point is capturing the shock, very sharp kind of thing. But multi-phase flows, by definition, you always have that kind of so-called discontinuities or shocks, even at low velocities. Can we really capture that? How to solve this equation? If you solve this equation precisely, one should be in a position to really distinguish what is density, what is viscosity, and other thing. But anyway, when you are solving that equation, we cannot directly solve it. You always have some source term, compression terms, or variety of ways to match that kind of line. For that purpose, if you are using only by volume of fluid method, what you do is, instead of this, because think of this is first mesh, second mesh, third mesh, fourth mesh, fifth mesh. Volume of fluid means some kind of volume in an abstract way you are filling. This entirely liquid. This entirely liquid. Here, only this much portion is liquid. But what you do is, because you don't know, it might be in this way, it might be in this way, it might be in this way also. One can fill it. What is that effective way you can really fill? The rest of the liquid captures your interface. So droplets supposed to be of this over some time, but what you solve is solve like that. So always step kind of things you will see in some sense. Can we really avoid the step? Yeah. So I'm referring like, instead of capturing this entire red line, you fill something like a colored function, the volume of fluid function, and rest of the cell based on how much volume it occupies, one will do. When you have that kind of sharp jumps, calculating surface tension becomes non-trivial task. If you don't calculate surface tension, all your two-phase system completely gone. So usually when one solves, they always get numbers like, yes, liquid is present in the mesh. When you are solving the transport equation 1, 1, maybe 0, 0, 0. But wherever gas liquid kind of interaction is happening, you will get some numbers in between 0 and 1. And based on how clearly you fill those numbers, one will be in a position to get this red kind of interface. Though at abstract level, I might be in a position to show some red line, but where exactly I need to put that red line to capture interface? Why? Because when I'm showing 0.5, this entire 0.5 means how much volume I can really fill. That 0.5 volume means it is more like fill the bottom half, leave the top half. Something like fill bottom half, leave the top half. That possibility is there. I can fill the blue color with the left side, but don't fill with the right side. Maybe put some diagonal line, fill that bottom diagonal line 0.5, top one left, or maybe some other thing. So all these VOF techniques, improvisation and other thing is how carefully I can really put that color and is it really making sense? If I am in a position to do that, we are successful. Otherwise, whatever solver you pick is going to fail. Second thing, by any means till now, at OpenFOAM, that successful interface capturing is not possible. You always have better and better kind of thing, but finding complete solution is not possible. If one can do that, they will be in a position to always write the complete velocity field is how much alpha value multiplied by liquid velocities, 1 minus alpha multiplied by gas. Similarly, pressure, density, mu, and other things, one will approximate. So the crucial challenge for multi-phase flows is, can I really give that alpha field or F field successfully so that the rest of the flow simulation one can capture? So there are variety ways. That's the thing what I'm saying. I may have one, some grid cell might be having 0.6. Should I fill it in this way or should I fill it in that way? We don't know. Maybe this is the interface what we would like to really capture, the gray color kind of thing in the A. If some successful simulation is there, it must be something like tracking this line, filling that gray. But there are variety of possibilities. Maybe fill this horizontal, fill it vertical, fill it horizontal, fill it vertical. Line by line, if we are going to fill, that's what we call slick kind of thing. Basically, this slick is acronym for this line kind of reconstruction procedures. Maybe VOF kind of thing, just horizontal, vertical kind of thing. So instead of having this kind of the gray color thing, A, when you are solving, you may be going to get C kind of picture. C color kind of picture means instead of this interface, your interface comes in that way. How much you may refine? There always be some zones where you are going to mess up. There is something like piecewise linear interconstruction kind of reconstruction is there. Then in that case, the same problem, maybe one might be going to get that. If that interface is gone, your chemistry, first of all, gone. Your heat transport is gone. So to summarize, even before beginning, what is interfoam? Interfoam never does this reconstruction procedure. Instead of that, it just smoothens the field. Alpha, whenever it is something like 1.6, can I really use some kind of Gaussian filter? Put something like 0.8, go ahead, smoothen. That means already there is a big error involved in that. It's okay for industry kind of research in some sense, but pure kind of research schemes and other kind of thing, it is a bit bad. How much validation one may do is not going to capture correct things. So what interfoam does is, sometime back we have seen del alpha by del t plus divergence of alpha u is equal to 0. One has to solve purely hyperbolic equation at CFD. You will always add additional divergence terms. The divergence of alpha L, alpha G, VR. this kind of additional terms, you add and solve that. By doing that, naturally you smoothen the interfaces, create additional errors, which at VOF kind of techniques, what people call parasitic currents. It shows additional convective motions around the system. That is the first indication that the solver is behaving very badly. Though you do not have any convective motions around that bubble because no evaporation, but still you start sensing some kind of evaporation kind of events happens. Indicates that solver there is some problem. Okay. So instead of VOF, people go with level set, club VOF with level set, and so on, so kind of strategies. CLS VOF kind of things people use. Overall, the algorithm, how it really goes is, you will have always some initial data. You want to calculate next time step. For that, you begin your pimple loop. I think in the last 1.5 days, you must have learned if you want to integrate this volume, volume equations like mass, momentum, energy kind of things. One of the popular technique is pimple algorithm, PISO, pimple, this kind of solvers. Basically, what you do is you begin at a time based on the initial conditions. You solve alpha equation with certain kind of flux limiters, smoothen the fields and so on. Then go ahead, calculate your properties like density, alpha, viscosity, whatever those things. Then use that information, solve your momentum equation. Once you solve that momentum equation, you go to maintain incompressibility equation or mass conservation. So you go use your projection technique via PISO loop, pressure implicit kind of thing, what you have like. Once you solve that, you find out the errors, go back, increase the time, again advect alpha equation, come back, repeat that. That is the way the typical interform works. Whenever there are some turbulent motions and so on, you will have this LES, RANS kind of things. Naturally comes changing your dynamical properties. Maybe at the mesh level, maybe at the fluid properties, like instead of dynamic viscosity, you use turbulence viscosity and so on, so things. So overall algorithm goes in this way. You have initial data. You want to increase in time. First solve alpha equation, volume advection. Done. Go with your momentum, go with pressure projection and repeat the thing. And typically the structure, if you are going to look at, it will have something like typical system constant 0. And system means you will always have your control dictionaries, decomposed power if you are going to use multi-phase kind of things, the schemes, and also what kind of algorithm you are using those solutions. Constant, you will always have this transport properties where you will have additional things in terms of defining your set fields. Wherever fields are present, like gaseous phase, liquid phase, there will be something like set fields where you will really specify where you would like to have this, the phase information. Zero files, where your velocity, temperature, pressure, and so on. In addition to that, you will always have additional alpha information when you are using multi-phase. So what you have to do is, in the afternoon class, our TS will work out or perhaps show you. First execute them. You will be first comfortable. Once you create that, you will see some kind of animation on Paraview. Try to sense the density, velocities, what are the new files coming into picture. And one dam break example, other one is capillary rise. Try to change two cases like viscosity increased by 20 times. Is the same solver working? Are you in a position to really capture, or is it going to do some other kind of issues? Increase, change the domain size, don't change the grid. What is happening? The liquid supposed to conserve, but is it diffusing out of the system? Instead of seeing something like liquid, over the time when you are simulating, the liquid content, a kind of artificial evaporation happens in the system. So that way this particular solver works. First, try to visualize it, okay, in the afternoon. If that happens, then we will go ahead, look at multi-phase Euler flow. So that is the first part. So any questions till now on that? We can learn a lot of solvers, but the background is more complex kind of thing and depends on which solver one will pick it. Snehal, would you guys like to take that workout examples? One, would you like to show now very quickly, 5 minutes kind of thing? So that first they will see, after lunch they will come back because you are showing one example for 5 minutes. They will first try to understand the structure. Then we can again reintroduce the next one. No, on your account, just show it. Whatever you have done, they are not going to practice now. That just first go slow, step by step, show them, see, these are the files, what we will have. I'm going to compile. When I run, see this kind of output is coming. Let us open it ParaView. So these are the fields creating. See, there is something like alpha field. Just show that animation and then again re-summarize zero, constant, system kind of files. What are the new things? Why don't you look at it, have your lunch. Once you come back, first explore that. And after that, again, we will take care of it. Okay.
Hello, am I audible? Okay. First we'll look the solver return form. So actually, for all the materials are there in the test user one. So in that folder, I'm going to first run the interform solver. Can you see the screen now? So these are the three folders, that is zero folder, which shows you the initial conditions. see, these are the initial conditions. Alpha water, that means what is the fraction of water initially it is there in the domain, then a pressure condition and the velocity condition. So you can see what is there inside the folder, inside the file. So these are the boundaries of the domain. That is, there is basically a rectangular box, and these are the boundary condition. On left wall there is no slip boundary condition. On right wall, right wall and lower wall also there is no slip boundary condition. In atmosphere, uh, there is a atmospheric pressure like condition. So first I will show you how the domain looks like. So what we'll do, first we'll run the code, and then after that I will show you in Paraview. Okay. So now I have created the block mesh file, and I will run the solver. So done. Um, these are the results for each time step for the simulation. So we need to transfer this result to this system so that we can view in Paraview. So initially you can see this is the domain. Thing.
Set fields.
Yeah. I'll run it again actually. Oh, okay. So actually there were set field command missing. So I run it again and you can see this is the initial condition. This is the water column and how it will break. See.
Red to blue kind of thing. Whenever those mesh resolutions are becoming bigger compared to the field information ranges, immediately some kind of artificial evaporation of field is missing out of the system. So this one fades out. That means it can't really capture the things. And whole challenge of any multi-phase system is, can you really retrieve? So let's go for lunch. And this example, just give it a try. Come back and that example will be available at your local level. Copy that into your directory, give it a try. The two questions, whatever I have asked, give it a try. So we will catch up again at 2:30 p.m. Okay?